Hello everyone, I'm Zach Romano, and today I'm going to be presenting the 2012 paper on cross-VM side channels and their use to extract private keys. This is a paper by Yingquan Zhang from the University of North Carolina with the help from a few others. So a quick run through of what we're going to be going over today. I'm going to give you an introduction to this paper and why it's relevant. I'm going to go over some of the background knowledge that might be required to understand this paper. We'll go over how they implemented this side channel attack, the results of the attack, and how one might prevent it. And finally, we'll wrap it up with some quick and closing notes. So the whole purpose of this paper was to extract a private key from another VM hosted on the same physical server. This is done via an access-driven side channel attack, and the purpose of it was to really get an LGAML decryption key from a victim running libcrypt. Libcrypt is a very popular cryptographic library that is very widely used at the time. And this paper is novel because it was the first to do this on a multi-core device virtualized using a modern VM manager. In particular, this paper focuses on Zen, which is very widely used by a lot of the major cloud providers. So this type of attack would affect AWS to Azure and Rackspace, so it could be extended to millions and millions of customers. So in order to understand this paper, you will need to have some background knowledge on hypervisors in VM. I will quickly review them here, but we definitely assume that you have some prior interaction with them. So a virtual machine is a virtual computer system with its own CPU, memory, network interface, and storage created on a physical hardware system. So if we look at this picture on the right, we can see that our physical computer is down here, and there's numerous virtual machines running on top of it. So if you think about a cloud provider, they have very strong physical machines. So this host is a very powerful computer, and it's capable of running numerous virtual machines on top of it. And then additionally, there is a hypervisor, which is kind of what separates the virtual machines on the physical computer and manages the physical resources. So if we look at this picture here, we can kind of see that the hypervisor, Zen in this case, is sitting in between the physical machine and these virtual machines. So the virtual machine kind of goes through the hypervisor to request resources, and the hypervisor is what allows the virtual machine to access the memory, access the CPUs, and acts as a scheduler to give each one of them access to resources. So this paper really focuses on side channel attacks. So what a side channel attack is, it's an attack on information from the implementation of the system rather than from a weakness in the actual system. So you might think of, this isn't really a weakness in an algorithm that they implemented. It's, they're vulnerable to a cache attack or a timing attack. Someone can monitor the power usage of the actual machine or the electromagnetic or acoustic signature from the machine. So there's kind of three main types of attacks used to get cryptographic keys. There's time-driven attacks, which use, this is used when a cryptographic algorithm execution time is dependent on the key. So you might think, if a key of 1, it takes 1 second, a key of 2, it takes 2 seconds. You can see how that could easily be used to deduce what the key is. The next type is trace-driven. So this is where you measure the power draw of the machine, the electromagnetic or acoustic signature. And this is kind of where this image on the right comes into play, is researchers were actually able to set a phone next to a computer and measure the sounds that the processor made and able to extract the private key from that computer. So that seems almost like science fiction to me. A person might be able to come into your house with their cell phone in their pocket and just listen to the sound, have it record the sounds that your processor is making and steal your private information. So it's almost like if they expand on that, no one would ever be safe. And the final type is access-driven, which is what this paper will focus on. And this is where an attacker runs a program on the same device and monitors some shared resource. A lot of times this is a shared cache. So that's really what this paper is going to be focusing on. Two VMs are running and they share the same physical cache, and we can measure that. So a quick overview of this attack. The goal of this attack really is to extract a private key from another VM running on the same physical host. And we're going to do this by analyzing the victim's usage of the L1 instruction cache. So if we kind of look at this picture on the right here, we can say, maybe this VM is our attacker and maybe this one is our victim. They both go through the hypervisor that schedules, who gets to use which core when on our physical machine down here. So, maybe the victim or the attacker does something, sets something up here in the L1 cache that allows it to monitor the next time when the victim uses it, and the attacker can run again and say, okay, I see the delta here. I can induce what exactly that the victim was running. So there's kind of two major stages for this attack. There's the measurement stage, which is seen here, and the analysis stage. So the first step really is to measure the usage of the instruction cache by the victim. And then with that data, we're going to classify patterns in the cache usage. This is your machine learning, really saying what exactly they were doing. And then with that data, we're going to reduce the noise in it. So there's a lot of misclassification or errors from the machine learning model, and we're going to have to reduce the noise, and we're going to use statistical analysis to do that. And finally, we need to reassemble the code path. So once we know what commands the victim was running when, we need to reassemble how they actually went through the code and ran it. And so this is going to be used. This is going to be calculated using graphs and greedy algorithms. So now we're really going to talk about who this attack is targeting. So the architecture that this is really focusing on is modern multi-core processors without SMT enabled. SMT is simultaneous multi-threading. They focused on processors without SMT enabled because there's already been a lot of attacks shown on that, and many cloud providers intentionally disable this. Additionally, we're going to focus on modern x86 architectures running Zen and their usage of the L1 instruction cache. So this is a very modern architecture used by all your big players in cloud providers such as AWS or Azure. And finally, we're going to induce that this attack has to be done on another VM running on the same physical server. So we will need to be in very close proximity to who we're targeting. So now we're going to kind of talk about some of the assumptions for this attack. So the first and kind of main assumption that we make here is that the attacker can either penetrate a VM or host a VM on the same physical server as the victim. So you need to be on the same physical machine. Next, the attacker is unable to take control of that entire machine. So if they could do that, there would be much simpler attacks that they could perform and do this much easier. Additionally, we assume that they are able to access a copy of the victim's code and able to analyze the code that they're actually running. So this is going to be used to train the machine learning model. And you might think of like an internal company attack. So maybe I know I can have access to the Git repository of another team, but they're not idiots. They didn't check in all their passwords. I can't see their private keys. So I could use this attack to kind of penetrate and determine what their private keys are. And finally, we assume that the victim is running a cryptographic algorithm whose code path is secret key dependent. So key A is going to take a certain path, and key B is going to take a different path in the code. So what we're really doing here is analyzing the code path that a victim is taking. And so I kind of like to point out that this is a very sophisticated attack that has never been demonstrated in the real world. It's probably not going to happen against the average user of a cloud service. This is really probably going to be, an attack that's going to happen to a government agency or by a government agency. So you have to have a copy of the victim's code and host on the same physical device. That those aren't trivial tasks and would be very hard for someone to do against just a random cloud provider customer. So some of the challenges with this attack, there's kind of three main challenges. The first one is observation granularity. So basically, the attacker needs to ensure that they frequently alternate execution with the victim on the same core. So that can be quite challenging because you're at the liberty of the hypervisor's scheduler. The next is observational noise. So you kind of have to decipher when it's the victim using the L1 cache and not, something as the hypervisor, because it has to use the same physical cores as well. And then also, whenever you're training your model on the victim's code path or with the victim's code, you have to do that without changing the code path at all, or as little as possible, because any changes you make to their code would vastly disrupt your results. And finally, there's core migration, which basically you have to determine if the actions that you're monitoring are associated with the victim or just some innocent bystander VM that you happen to be analyzing results on as well. And so really here, another issue here is that you can only spy on the attacker when they're assigned to the same physical CPU. So maybe the scheduler is scheduling your code on one core and the victim's code on another core. You're not going to be able to measure any of their execution if that happens. So let's get into the actual attack here and how it's implemented. So if you remember, the first step is kind of measuring their instruction cache usage. So a basic technique for doing this is kind of filling the instruction cache with your own instructions and then kind of waiting for the victim to perform their actions and then refilling it and measuring the time that it took to refill it. So filling the instruction cache, that's called priming, and then measuring the time it takes to fill the instruction cache is called probing. So the basic implementation here for an access-driven cache attack is to prime the cache and then later probe it. So priming, as I mentioned, is kind of where the attacker just fills one or more cache sets. They fill it with all of their own instructions, and then the next step is they wait. This is the idle step, where the attacker waits for the victim to use the instruction cache. And then finally, the attacker executes again, and they probe the cache, so they time the duration that it takes for them to refill it or reprime it. And based on that, they can learn, they can determine the usage from the victim. So one major problem here is that we need to frequently alternate execution with the victim. So if we kind of look on the right here, maybe this is our attacker again, and this one is our victim. So they're both end up alternating on core 1. So a problem that we have is that we need to very, very frequently have the attacker execute code here and then the victim. And ideally we want to alternate as much as possible. We want it to be, attacker, victim, attacker, victim. And this is very, very important to the results of this process. And so basically how we're able to accomplish that is by interprocess interrupts, or IPIs, which in a multi-core system, this allows one processor to interrupt itself or interrupt another processor. So basically what the attacker does is they set up an endless loop that is issuing these interprocessor interrupts, and they just are sending them repeatedly, which gives the attacker control of execution again. So you might think the victim is executing, then we issue an interrupt, and then the attacker takes back over. So this allows us to very quickly alternate between who is executing on the core. So next we're going to get into some sources of noise. So our process here is for measuring the cache is great, but obviously not perfect. So there's a couple of main sources of noise. So first we'll talk about hardware sources of noise. The main one here is TLB misses, which cause very high probing results and inaccurate probing results. So basically what a TLB is it's a cache that translates from virtual addresses to physical addresses. And you can think on the first probe that we do, there's always a TLB miss, so those timings are going to be abnormally high. So we always discard the first probing result. Another sort of noise is from software, so we can think of, there's probably going to be more VMs than just the attacker and the victim on the physical host. So maybe we're measuring the execution of some, bystander VM over here, and we really don't want to analyze their result or their execution. So we really only want to focus on the victim. So we're going to have to filter them out somehow. Another software source of noise is that Zen, the hypervisor, it has a tendency to schedule VMs, different VMs on separate cores. So kind of in order to avoid this sort of attack. And what we can do to kind of get around that is that there's this administration VM that runs on Zen, which kind of is what allows cloud providers to control the hypervisor, control which VMs are running on it. So what we can do is if we provide a pretty big load on this administration VM here, or DOM0, we can force it to run on all of the cores, and thereby increasing the chance that VM1, our attacker, and our victim end up executing on the same core. And so one way that we do this is by providing a load on DOM0, and we do this by sending it a lot of network traffic. So maybe we're sending a bunch of requests to the attacker or a bunch of requests to the victim, and this administration VM is in charge of all of the network traffic. So that's going to cause it to have a higher load to distribute the network traffic, and that will vastly increase our likelihood that these two end up on the same physical core. So now we're going to talk a little bit about the square and multiply algorithm. So this is kind of the code that we're going to be analyzing and trying to determine the path of. So this really isn't the main point, so I won't spend too much time on it. But really what this code block is used for is for decryption algorithms, and the path that it takes is dependent on the actual private key. So if you know the code path that this takes, you can induce what the private key is. And this is kind of basically the whole point of why we're doing this, but the algorithm itself is kind of besides the point. The main things that you really need to know here is that there's kind of three main different operations here. There's the square operation, which we'll denote with S, the mod reduce operation, which is R, and multiply, which is M. So, you can think of a code, if your key is 1, we might take this. If your key is 2, we might take this down here. So now we're going to talk about how we actually analyze which path that they took in the square and multiply algorithm. So we're going to use this using a support vector machine. A support vector machine is believed to be one of the best off-the-shelf supervised machine learning algorithms. So they're very widely used and believed to be pretty easy to implement. And what we're going to get from this is we're going to get labels from the prime probe results that we got earlier, and we're going to label them as either a multiply, a square, or a mod reduce in the square and multiply algorithm that we saw earlier. In addition to these labelings, we're also going to get a probability of its confidence. So, maybe if it's a 1, it's very, very confident that it was a multiply, or if it's, a 0.1, we're not that confident that our results are correct. And so in order to train this model, we're going to set up a machine with a very similar architecture to the one that the cloud provider is using, and where the attack is actually going to be performed. And we're going to run that code and analyze it with our own keys and kind of train the model for a while on what the data should look like. And it's worthwhile to note that in order to do this, you have to make a slight modification to the victim's code in order to train this. And so really we want to reduce the amount of differences between the code that we're training on and the code that's actually going to be executed. So now we're going to talk about some noise when we're trying to classify what code path that the victim was taking. So there's kind of two main sources of noise here. The first one being classification errors. No machine learning algorithm is perfect, so the SVM is certainly going to output a few misclassifications, so we're going to need to correct those somehow. And the next one is the presence of prime probe results that are of no interest to the attacker. So, maybe either the VMM or Zen was running something, or a bystander VM was running something. And we're going to kind of discuss in later sections on how we mitigate these. So now, if you remember, the next step in our processing is to actually reduce the noise from our SVM results. So we're going to do this using a statistical model called a hidden Markov model. And basically what this is going to be used for is to find all the errors in the classifications from the SVN. So it'll take in the labeling that the SVM gave it and the probability, and it's going to output a new classification with hopefully fewer errors. So what we can kind of think of here is, maybe 99% of the time we have sequences of, square, 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 square. As we can see here, maybe we have, 5 S's in a row, and that's almost always the case. But in some of the results, we see, this multiply in the middle there. We can probably induce that that's not supposed to be there, and that was an error in the classification from the support vector machine. So from the output of the HMM, we get 7 classifications. So we take the 3 classifications from the SVM and the probabilities that it input, and we convert them into these 7 classifications. So we have this L, which designates a low confidence, and we have this lowercase s, m, and r, which is medium confidence that it was a square, mod reduce, or square, multiply, or mod reduce. And then we have our capital S, M, and R, which say, these are very high confidence that it was a square, a multiply, or a mod reduce. And we can kind of see a picture over here denoting how the HMM model works here. So, you take your inputs and you end up at one of these 7 classifications. So after we run through our hidden Markov model, there's still a bit of post-processing that we want to do. So here we're basically just going to be doing some more statistics on our data. So we can say that a sufficiently random private key should have a similar number of zeros as it does ones. And if we refer back to our square and multiply algorithm that we're analyzing, we know that a 1 induces a square and a multiplier operation, whereas a 0 only induces a square. So we can say that our results should have a square to multiply ratio of about 2 to 1. So many of the results are going to have crazy ratios out there that we don't care about. So we can kind of filter our result sets to only ones that are in the general range of about 2 to 1. So with that, we can kind of say that this method might not work if you had a private key of all zeros or a private key of all ones. I guess you could defend against this type of attack if you wanted to implement a key with zeros or all zeros or all ones, but nobody does that in the real world, and you're going to be susceptible to a whole host of other types of attacks if you try to do that. It's probably going to be the first thing someone tries if they try to just brute force your key. Additionally, we can improve detection by excluding any sequences of multiply-multiply. So multiply-multiply never occurs in the square and multiply algorithm, and so any results that are suggesting that, we can just automatically exclude. And this will vastly filter down our results to only code paths that are the square and multiply algorithm. So the final step in our analysis here is to stitch back together the code path. So if we think of these HMM outputs as a fragment, we can kind of correct any errors there by comparing across the fragments. So the beginning of this small batch of operations is going to have appeared many times. So we can compare across them and make sure that that they all make sense and align with each other, and find any obvious errors in them. And then finally, we're going to stitch those fragments together to have a full code path. So there's kind of 3 main steps here: the cross fragmentation, error correction. So that's comparing those fragments and making sure that there's no errors. And then the next is fragment stitching, which is we basically create a graph and employ a greedy algorithm to find the maximum spanning sequences This is kind of done in batches so that we have several different maximum spanning sequences. And that leads us into our final step, which is combining those spanning sequences. So combining the results of all those batches and comparing across them to find any errors. So throughout all of those batches, you should have a pretty good idea of what the private key is. So finally, we'll look at the results of this. So they were able to break a 4096-bit key with enough accuracy that they only had to brute force roughly 10,000 keys. Just to put that into perspective, there are 2 to the 4096, which is the number of possible keys that could be in a 4096-bit key. That's 1 followed by 1,233 zeros. So yeah, that's a 1 with over 1,200 zeros. And just to kind of put that into perspective, there are only 10 to the 72 or 10 to the 82 atoms in the universe. So this is a pretty substantial reduction over a massive possibility of keys. And this only took them 6 hours to collect this data. So that's really not a lot of time to have to be on the same physical host as your victim. And then additionally, they also tried this with a non-work conserving scheduler. They only had to search 6,600 keys then. And so basically a work conserving scheduler tries to keep the scheduled resources busy. So in a non-work conserving one, some of your cores might be idle longer, or your interrupts get descheduled more often, so you don't have that frequent alternation between the victim and the attacker. It might be the attacker executes and then has a long gap, and the attacker executes again, which you obviously would not get any interesting results. So with the non-work conserving scheduler, they had to collect data for 45 hours. But they were able to search through fewer keys. So some final notes on the results that they showed. They were generous to the attacker in a few different ways. So the main way that they were nice is that they assumed that the victim would often be performing this decryption algorithm. So they basically assuming that the attacker or the victim is doing this operation very often. They're not doing it once a month, or you would have to collect data forever, right? So they're assuming that maybe the attacker has a way to trigger this action. So maybe they can send a request into the victim, and that request is going to result in the decryption algorithm running. And it's worth noting here really that even though it seems like they're kind of saying, okay, the victim's only doing decryption, that's not that would never happen in real life. Still, the exponentiation that we're measuring was still only 2% of the total execution of private key decryption. So at a very minimum, they were excluding 98% of total execution. So this is kind of boosts their credibility that the victim wasn't just only running this square and multiply algorithm. There was a lot of execution that they had to filter out in order to get these results. And just some notes on prevention here. This probably isn't something that the average cloud user needs to be worried about. This really only would be relevant for very, very highly sensitive data that you want to keep private. And there's really a few easy steps that you could do to keep it private. So just keep your code base private. Don't let others see your Git repository or your code base, and they will not be able to perform this attack because they'll never be able to train their machine learning model. Another suggestion is to not virtualize. So if you're never on the same physical machine as someone else, you could never have this problem. So maybe you use a private cloud and ensure you have your own dedicated physical machine. And finally, you can modify core scheduling to how it handles these interprocessor interrupts. So make sure that the attacker can't alternate execution as easily as was shown here. And actually, the Zen scheduler has been updated since the publication of this paper to try to reduce the ability for an attacker to do this. And there's one final one that I didn't list here because it's not really ever used, but you could also not use a decryption algorithm that is code path specific, so you could use one that doesn't have any branches or one that wouldn't allow a user to track the code path, but those really aren't used in the real world because they're very slow. Most people are using one that is code path dependent, such as the LGAML decryption scheme. So some quick closing notes. I just want to reiterate that the main point of this paper was to show that it's possible to analyze the code path on another VM and use that code path to determine a private key. And so you can remember the basic steps that we were able to perform to do this, where we just measure the instruction cache usage, then we analyze those results by classifying patterns, reducing the noise, and reassembling the code path. And the authors really wanted this paper to serve as a cautionary note to those who rely on virtualization to guard their highly sensitive secrets. Maybe a government is virtualizing and they don't realize that they're susceptible to these types of attacks. Maybe another foreign government is trying to perform one of these on them. And really they just wanted to use this paper to provide motivation for the research community to look into this more. Maybe it actually is easier to perform this than they thought. Maybe you don't need to know the code base. So they were really hoping to spark interest in this topic and get people talking about it. I want to thank you all for watching my presentation, and if you have any questions, feel free to contact me at my email here. So thank you.